We are going to start about our something called finite dimensional vector spaces. Finite dimensional vector spaces. So you are already familiar with it, sort of thing. So basically, what we are trying to study is linear transformation. Transformation you might have been aware of if you have studied some portions of matrices or linear transformation in matrices. But we are studying it from some basic theories, and it's also sometimes synonymously called as linear algebra. So there is both have not only finite dimensional vector spaces, we have also infinite dimensional vector spaces. So to begin with, how we can see our characterization of these finite dimensional vector space here. I want to emphasize this space also has some part of geometrical element in it. So because this intuition helps us to visualize the constructions of geometry. That's somewhat deliberate. So to begin with, before we are going to say what are spaces, so we have to define something called fields. Just like we have number fields in mathematics, we have number fields, or those number fields will be real number fields, there will be fields of rationals, there will be fields of complex number fields is the most generalized set. So use a field spans a certain set of number fields, and we have some operations on these number fields, whether it's scalar addition, subtraction, multiplication, whatever rules. And so you will not use the numbers if you follow this book. So the book which you are going to follow is by Helmholtz. I forgot to say it. Helmholtz book. It's a very standard book. Finite dimensional vector space. I forgot, by Helmholtz. So if we just follow Helmholtz, he is more comfortable with using the word not numbers. He uses numbers as scalars. It has some advantages. So we will not talk of, when we talk of finite dimensional vector spaces, we don't talk about numbers. We will talk about them as scalars. This is another way of saying we are talking basically about numbers. And these scalars can be real numbers, or they can be complex numbers. Now we are going to see on how we can operationalize them in terms of some generality. Operationalize them the way in your earlier classes you might have studied. When you study arithmetic, you have simple operations of scalar addition, scalar multiplication, distributive property, and so if we assign these numbers as scalars which compute these real and complex numbers, and if we define some set of operations, for example, so if we have a is that to each pair, to each or to every pair, and to every pair alpha and beta which correspond to scalars, then alpha plus beta is scalar addition in some sense. So if we they correspond to So alpha and beta are scalars, and alpha, so you can have some properties like properties of commutativity. For example, we say that addition is commutative. It means if you change the order of the elements vis-a-vis these scalars, it should not, this relation should hold. If you change alpha with beta, beta with alpha. So this is one of the properties which you might have, if you recall, they are commutative addition. So the other property is addition is associative. Addition is, so if you have another number alpha plus beta plus gamma, you can say it's alpha. So it will not change. So if you, the order of, if you just place it like this, the properties of whole this will not. So this is another property. And the third property is that, for example, there exists a unique scalar which you normally take as 0, such that if we add this scalar to this 0 or scalar, any scalar 0 to any of them, so it will be equivalent to, so it will not change anything. It will not change anything as far as this thing. And we should also be able to find a number or another scalar such that it's equal to, such that alpha. So this is, so if we, in this BA, we have this sort of properties. Now if we take, this is for in some sense additivity properties. We have of these numbers or scalars spanning a certain field. Okay, so these are these properties. Now the other properties are properties of commutativity. Again, in case of commutativity, what we are going to say, again, you know it. So if there are alpha and again alpha and beta, so this is A and now this is B. So we have, these are, we have enumerated the properties in terms of scalar addition. Now we are going to see it in terms of multiplication. So the properties are, for example, alpha beta is equivalent to, so again this is commutativity. The order of these elements, if we change the order, it will not change the properties of this thing. This is property 1. Property 2 is, so it's multiplicative. It will be again, so it's multiplicative. And property 3 will be, it's associative. It's associative. This is associative property. This is commutativity. And the third property is, just like we have a unique scalar here 0 in terms of addition, there should be a unique scalar which is called unique scalar. Here the unique scalar was 0. Here unique scalar is, for example, a number called 1, such that if you multiply it by that number, it will not, alpha into 1 is equal to, you can get it. So the multiplication of that unique scalar with this scalar, it will not change. It will leave it intact, the same as it was previously. And the last property is that we should have a unique number such that if you multiply it, or we should have a unique scalar such that if you multiply it by that unique scalar, it will give you identity element 1. Got my point? So it's like this. Or you can also write it like in terms of this alpha inverse is equivalent to 1. So this is A, this is B. Now the third property C, because these combination of properties which in terms of scalar addition and multiplication, and now we are going to say multiplication is distributive, with respect to addition. So what do we mean by that? So alpha into beta plus gamma will be equivalent to alpha beta plus alpha gamma. So multiplication is with respect to addition. So this is it. So you can have this is scalar multiplied. You can have this. Now, what we are going to say, this property A, B, and C. Property A, B, and C. If the numbers are set, they are satisfied, and together, this is called as field. This is called as, so any scalars or any addition, if they follow this property, and this property, they span a, we call it, they span a field. They span a field. This is it. Now the point is, now there come some exercises. For example, if you see to the text, look here. You see to the text, there are some exercises. If you read the preface of the section, he's saying that, for example, if I read, here's a very interesting sentence for it. For example, so if he says that if an exercise is imperative, one is imperative, another is declarative, the third is interrogative. Imperative means what? It should imply. Integrative means whether you have to prove whether it exists or not. You have to show it. You show it like this. Imperative, it should imply. Declarative, you just see whether it is. So he's saying the third, there are a lot of exercises in the book. So the declarative exercises are sort of challenging, because he is neither saying that they are, so you need some effort to show it whether they are right or, so he is open-ended. So in the sense that if you have some examples, so question is that if we under this set of assumptions, under this, if you define fields in terms of this, and this, and we can construe some examples or certain cases, do they satisfy this algebra or not? Okay, they may be satisfying in examples or they may not be satisfying. So if they are satisfying, so you have to show by examples. If they are not satisfied, you have to show the contradiction. Okay, or if they are satisfying, if you change the assumptions, starting assumptions, you have to see. So in the different cases, you have to just work out different problems. For example, so almost all laws of arithmetic. So if I just first example. So almost all laws of arithmetic are consequences of actions defining a field. That's fine. All laws of arithmetic are consequences of actions defining a field. True that in particular, if F is a field, F is a field, and alpha, beta, and gamma belong to that field. True in particular, if F belong to field, then the following relation should hold. So you have to show it. So if alpha plus beta is equal to alpha plus gamma, alpha is equal to gamma. Or alpha plus beta minus alpha. So it means it is equal to beta. And beta minus alpha is equal. So you know it from simple rules of arithmetic, you know it. But the point is, you have to see it. You are imposing a construction on those very number fields. From that constructions, you have to prove it, not from your that intuition which you have got from your earlier classes. You think that you are imposing some properties on numbers, on those numbers which act as scalars, which constitute from those very fields, and which have these properties of addition, and distribution, and commutative relations. So from that, you should be able to prove it. Got me? As a construction, not as you have you know it. It's true. That simply you can. So you can sometimes question it. Got my point? So that way you have to see it. So I'll not do it. So you just better think at your place and try to see it. Or E is this. F is like this. And if alpha beta is equal to 0, either alpha is 0 or beta is 0, or both of them are 0. So these are different examples. At least you read them, what he wants to say. Now we are coming to our main the thing. Since we are talking of vector spaces, so we are coming to our. So this was fields. Now we are going to define vector spaces. We are going to define vector spaces, and then we can just see how it will all work out. So what is the difference between fields and vector spaces? Again, first we are going to define what's a vector space. So vector space, again, the way field is defined in a certain way, and we impose some properties, and we arrive at how we describe the thing. In the same way, vector space is set V of elements satisfying following axioms. What are the axioms? First, the way we had here A, B, and C, we also have there A, B, and C. What is the so if, for example, to each pair, I'll not write the entire language. So to each pair X and Y of vectors in V, there corresponds a vector X plus Y such that number one, addition is commutative. Which means X plus Y is equal to. So you should always remember the thing is, which I want to emphasize is, once we say it is, you can construct a number field where addition may not be non-commutative. You got my point? So it's how we define the things. So it's always possible to define things in a non-commutative way. You can define a thing, for example, X plus Y is not equal to Y plus X. You can define a number field that way. And you just assign them properties and see what's the algebra and how things will work. So it's all constructing a sort of game. We define things like that. We define field in this way. We define vector space like this. So if you define things like that, then what will happen? This is our thing. Got my point? It's not that whether it's true or not. It's intrinsically true or not. That's not the point. It's how we define things. So that I want to emphasize. Otherwise, it will look trivial for you. It will look trivial. You know it already. So once you define things this way, it will make you will just see subtle points. So if it's addition is commutative, in the same way, addition is can be associative, such that x plus y plus z equivalent to x plus y plus z. Got my point? X plus y plus z is equal to, so again, this. The third point is, so there exists a unique vector, there is a unique vector v, or 0 called the origin, such that again x plus 0 is equal to x for every x. Again, so there exists a vector, for example, x plus minus x is equal to 0. This is property A for vector space. Now we are going to property the B part of it. The B part of it is to every. So now here it's scalar addition. Now we are going to multiplication. For multiplication, we can say to every pair alpha and x, where alpha is scalar and x is vector. So the first property is alpha into beta x is equal to alpha beta into x. It means that the order of it will not matter. If you take this vector inside the brackets or outside, the property should hold. And the second property is 1 into x is equal to x for every vector. The third property is, so multiplication by scalars is distributive. Multiplication by scalars is different. For example, if you have a multiplication, this is a scalar, this is x plus y. So this multiplication by scalars is distributive. The fourth property is multiplication by vectors is, but this is multiplication by scalars is distributive with respect to vector addition. The other is multiplication by vectors is distributive. Now this is multiplication by scalars. Now it's by vectors is distributive. So now what we are going to hear, we had vectors inside the bracket. Now we have scalars inside the bracket and multiplied by vector. So it will be, so multiplications by vectors is distributive with respect to scalar addition. With respect to scalar, here it was vice versa. So they are not somewhat independent actions. So they don't want to emphasize that they are logically independent in the sense that, so we say that they can be convenient characterizations for the object we are going to study. So we are going to study some objects, so we are going to characterize them by this or represent them by this sort of thing. And this and we can extend the same argument for real vector spaces. as well as complex vector spaces. So you can have scalars, you can see here, you can have scalars as well as vectors, and you can now, only in case of complex vector spaces, the things will become more complicated. How they will become complicated? So if you read this subsequent example in the book, you just look here. If you read the complicated example in the book here, so if you assume that these vectors are not simple vectors, they are complex numbers. So the things will become a bit complicated, because as a complex number, you have a plus iota, you have scalar and two scalars which is multiplied in a coefficient by a vector, by iota. So how will add the two? So you have two complex numbers, you have to have the two numbers iota. The complex part you will have one part, and real part you have another part. And then you have to define these operations separately. So things may become more complicated, and you have to check out whether it will be really true for this very thing will hold or not. So this is what I'll not just you read this part of the section at your place. So what he is saying that it's easy to verify all parts of our axiom A, B, and C. The C part, this was C part. Sorry, this is 3. The third property was C. So property A, property B, property C. So for complex vector spaces, it becomes a bit tedious. So it's as an exercise, you just see it, and we can call it as n-dimensional vector spaces. So if A, B, and C are the properties which satisfy for general vector spaces. So if you include complex numbers, then it's for complex vector spaces also, and you have to accordingly. So he used the book words of book the n-dimensional vector space. Now, now there are a couple of comments which are there in the book. So he says that there are some differences. The way we have defined it, property A, B, and property C, we have defined them for vector spaces. But we have previously defined them for fields A, B, and C. So if you compare and contrast the two properties, the way we define fields and the way we define vector spaces, there are some subtle differences and some maybe overlaps also. There are some properties which are in both of them, but there are some differences also between these. So what are the different similarities? For example, system A in both cases, A describes the additive structures of the system, B describes multiplicative structures of the system, and C describes connection between the two structures. So A and B can exist separately, and the property C is seen that the properties of A and B are in conjunction. You can see the properties are, and you can see the play of these two properties in the C properties. Now the point he is trying to say is that once we go So he's saying that those familiars might not have to study algebra. So algebraic term. So normally in the rules, how we construct the statements of algebra, the this property A is very much in use. And once we define, admit these scalars can also be, we also use them as somewhat operators. Somewhat, if you just read the books, mathematics books, scale, you are operating on something. For example, you can take it alpha is somewhat operating on this thing, like this thing. So in the former case, if it is fields, in case of vector space, if they are scalars are operating on some numbers, they are known as rings. They are known as ring. In the previous case, it was fields. In case of vector fields, it is ring. Rings, vectors, it's rings. In previous case, it was fields. And in the generalized concept, it's also called module. What's it called? Module. It's a more advanced definitions. Now, what he is trying to say is that we, for example, when I said that this becomes a bit complicated for when we the complex numbers. So what we will normally do, we'll take C2. We don't normally define these operations of scalars because there are some geometrical notions which are associated with how we construct vector spaces. Particularly in, for example, space R2 and R3. R3 means it's two-dimensional and R3 means three-dimensional. You can extend to Rn in principle, but as a sort of visualization, it's more helpful in that thing. And if we study modern quantum mechanics, whole of quantum mechanics, we define their Hilbert spaces. You might have heard Hilbert. So how we construct Hilbert spaces, we have to go through these vector spaces. And those infinite dimensional vector spaces. This is finite dimensional vector spaces. So how we arrive at Hilbert spaces? It's via, so the quantum mechanics, the mathematical foundations of quantum mechanics go through. So you first have to clear these very things. So this is the, so this is this point. So as a motivation for a mathematics, it's okay. So you study vectors, but it also has some relations to subject of physics also. How the mathematical foundations of quantum mechanics, they have roots in this way. Let's stop.